For this lesson, what we will be having is the nth order solutions for homogeneous, linear, ordinary differential equations. So I know it's quite wordy, but then you have to take note of those words. So again, nth order homogeneous, linear, ordinary differential equations. And then we will be taking up the first case, which is real, distinct, and the second case, which is real and repeated. We'll be discussing nth order, linear, homogeneous and non-homogeneous, ordinary differential equations with constant coefficients. Let's just say that these a sub 0, a sub 1, etc. up to a sub n minus 1 and a sub n, they are the constant coefficients. And then these are the differential operator. So this one, the nth order derivative of y with respect to x. So you can see that the nth order is placed in first and then followed by n minus 1 order and so on until the first order, until what you see here is just the y. So this represents the nth order differential equation, and then it becomes lower in terms of order. If Rx is equal to 0, then the equation is homogeneous. So let's just call this type number 1. And then if Rx is not 0, then it's non-homogeneous. This is type number 2. For today's lesson, we will only be discussing type number 1. For example, if we have 2y double prime plus 3y prime minus 5y is equal to 0, if I ask you, you can say this is a homogeneous, linear, because it's of the first degree, second order differential equation with constant coefficients. Whereas in this case, look, what is the order of the second example? Third order. What is the degree of that third order? So in this case, for the second example, you can see here that this is of the third order. Therefore, this one is simply non-homogeneous, linear, third order differential equation with variable coefficients. Let's go to differential operators. I know you've already seen something like this in your differential calculus and integral calculus. So for example, you have the differential operator D. This basically represents the derivative of y with respect to x, that capital D. So this one is the derivative of y with respect to x. Therefore, you can say here that the kth order derivative of y is the kth derivative of y with respect to x. So for example here, if, let's just say a, if a is equal to a sub 0, a sub 1, a sub n minus 1, and so on. So basically, these are the constant coefficient multipliers of the differential operators. So that's the nth order differential operator, and then it becomes lower until it's just the constant, right? Is equal to Rx. If that Rx is equal to 0, okay, we know that this is homogeneous. So if I multiply that A, the set of differential operators, with y, I know that it is basically solving for the differentials of y or the derivatives of y of those orders. So for example, we have here 3d to the third minus 5d to the second plus 3 parenthesis y. This basically means, so this one, this is basically 3 d third order y minus 5 d second order y plus 3y is 0. Or if you want to write this in terms of the Leibniz notation, the one we're used to seeing, it's basically third order derivative of y with respect to x minus 5 second order derivative, or basically just the second derivative. So this one does not have a d, it's just 3y. It does not have a differential operator. Again, with the differential operators, any linear differential equation can be expressed in terms of the D notation. So the differential operator notation. For example, y double prime plus 5y prime plus 6y is equal to 5x minus 3. So these one don't contain y, so it's okay to have them on the right side. This y prime is a derivative, second order derivative. So you can replace that with d to the second. And then this is first order derivative, so it's just d to the first, or you don't even need to write the first. So this becomes d to the second y plus 5dy plus 6y is equal to 5x minus 3. And then what you can do, you notice that all of them have y's, the variable y. You can factor it out to have this. We're basically just going through how they can be written and what the operations could be. So some of the properties of the differential operators, if A, B, and C are differential operators, then it follows that A plus B is equal to B plus A. What do you call this property, guys? Exchange places, it's commutative. If it's changed in grouping symbol, it's called associative. In here, you can also apply the associative rule. So you can start with A and B first, and then add C, or B and C first, and then add A. And then you can also apply the third, which is the distributive, AB plus AC. And then also, the associative rule in multiplication, you can start with BC first before AB. It's okay. Or AB first before BC. It's okay. It's the same. However, look at the last one. AB is not necessarily equal to BA. It only happens once when AB will be equal to BA if and only if A and B are linear differential operators with constant coefficients. I'll show you later on what I mean as we go along. Let's just take these for example. Let's just say A and B are both differential operators. You can see here, this is x times the derivative with respect to x. So derivative of, we don't know yet. Here, it's the second derivative with respect to x of, we don't know yet what variable. A plus B is equal to B plus A. So let's apply that. If we are to take the differentials of letter y or the variable y, we can say here that AY plus BY. So basically derivative of y plus derivative of y, but then the other one's b. So let's check if they're the same. A is actually x dy over dx plus the second derivative of y with respect to x. Is that equal to the second derivative of y with respect to x plus x times the derivative of y with respect to x? Are they the same? Yes. Basically, they are just the same. We apply the commutative rule. So it holds true. But then later on, I'll show you again why commutative rule does not really follow if they're not linear and with constant coefficients. So here, let's try this. You already see that there's y outside. So take note that d is actually the differential operator, d with respect to x. So I can say here that d plus 2, if I want to distribute, this becomes the derivative of y plus 3y, right? And then what I do is I use the distributive property. So derivative, and then there's another derivative. I can say that's the second derivative with respect to y. And then derivative of what? Of 3y. And then here, it's basically 2 times dy and then 6y. D3 is equal to 3 d, because if they're just constants, you can just bring it out. So I can see that this one is 3 dy plus 2 dy plus 6y. So when I combine all of them, you can say second derivative of y plus 5 times the derivative of y plus 6y. Now, all of them, guys, have y as the variable. So I can say the second derivative plus 5 times the first derivative plus 6 times y. I start with the inside first, or the two left terms first. What if what I do is this? D squared plus 2d plus what? 3d plus 6. And then y. This one will still give me d squared plus 5d plus 6 times y. So you'd say, sir, why don't we just multiply the left side first before we multiply the d? It's okay here because it's purely the differential operator and the constants on the left side. Just like this one. Let's start with the multiplying the right side first. So d minus a, this is dy minus by. So when I multiply, this is the second derivative with respect to y minus d by minus a dy plus a by. All right. Do take note that I can say here b dy because that the b there is a constant. I can bring out constant just like in your integral calculus, in your differential calculus. So here minus a dy plus ab y. And then if I factor out the dy, I can say this is b plus a dy plus a by. And lastly, if I want to bring out letter y, what I can do is this. D squared minus, this one can be written as a plus b, d plus ab, and then y. So you can see that there's a variable y we can factor out outside. So, I'm just showing you the possible operations in here. All right. So earlier, it's purely constants. Now, what if we're not dealing with purely constants? So let's deal with this one. So this will explain why I always do the right side first. So this one, dy plus x, y. Okay. I said earlier that commutative rule does not apply if it's not linear and with constant coefficients. So now, they are linear, yes, but not with constant coefficients. So when I multiply d with this, you can say, that's the second derivative with respect to y. When I multiply d to the other side, that's just the derivative of xy. When I multiply this, it's not dyx, it's x times dy. Do you see the difference? The order is important. X is on the left, so it should remain on the left side. Minus x squared y. D is equal to the derivative with respect to x. So if I were to rewrite this as the derivative with respect to x of xy, I can say, oh, that's two variables. Copy the first, derivative of the second, plus copy the second derivative of the first. What is the derivative of the first, guys? Isn't it that that one is actually a property that's equal to 1? And then this one, if I were to rewrite this as a differential operator d, that is simply dy. So here I can say x dy plus y is actually your d of xy, meaning this one is x dy plus y minus, so this one would then be, or could then be written like this. So here, you'll see that you'd be able to cancel out some terms, yes, but you'll be left with three terms. So this is d to the second of y plus y minus x squared y. So if you want to factor out y, you're left with d squared plus 1 minus x squared y. So now you understand why when I say it's not commutative, like here, when x is multiplied to this, the negative x is multiplied to this one, negative x comes first before dy. So that means the derivative only applies to y and not to x. Can you follow what I mean? That's why the order is important. But for products between constants and linear differential operators, we don't have a problem. The constants always go in front. It becomes a constant multiplier. But for variables, you can't just bring it inside, or you can't just bring it outside wherever it is. If it's inside, it should remain inside. If it's outside, it should remain outside. This one becomes dy plus xy. So the second derivative y plus d of xy. So if you want to separate that, this becomes what? Copy the first derivative of the second plus copy the second derivative of the first. If you want to move out so you can see the different forms, this one could be rewritten as this, right? Okay, last. So d squared y plus x dy. So here, if you want to remove the y, it's basically d squared plus x dy. So let's go to another principle, which is what we call the principle of superposition. In here, if y1 and y2 are two solutions of the differential equation, so any differential equation equals 0, then the linear combination, so c1y1 plus c2y2, is also a solution for any value of the constant. So any combination of y1 and y2 multiplied to any constants are also solutions. Okay, I'll show this to you as we go along. For linear independence, the functions y1 of x plus y2 of x plus y3 of x and so on are said to be linearly independent if the following identity cannot be satisfied unless all the constants are 0. So this is the identity. Just like in the superposition, c1y1 plus c2y2 plus c3y3 and so on until you reach cn of x is equal to 0. So according to the linear independence, if this one cannot be satisfied unless all constants are 0, this is linearly independent, right? So if the constant, so let's go to the second paragraph. If the constants, not all 0, can be found such that the above equation is satisfied, then the functions are said to be linearly dependent. So these are some examples at the bottom. I'll show this to you on the next slide. So let's try the first one. According to the principle of superposition, so C1 sine of x plus C2 cosine of x is equal to 0. Let's think of terms that will equate the two. When will sine and cosine be equal, guys? At 45 degrees, you're correct. However, this is a variable. It's x. So it should hold true for any value of x and not just 45. Am I correct? Because when you say, if it's 45 degrees, they're the same. So I just need to have C1, and then this is negative C1. Yes, if it's 45. The problem is, this is given to be x. So will there be any way in which they will be equal, apart from being 45 and then C1 minus C2? No. So they can only be equal if C1 is equal to C2 is equal to 0. What will happen is that 0 plus 0 will be 0. So going back to the definition, it is linearly independent because it cannot be satisfied unless all constants are 0. So if both constants are 0, that's when it becomes 0. So this is linearly independent. Let's go to number 2. C1 sine squared x plus C2 1 minus cosine 2x. Can that be equal to 0? Let's see. Recall. What is cosine 2x, guys? Isn't cosine 2x cosine squared x minus sine squared x? Am I correct in here? Therefore, this one, C1 sine squared x plus C2, 1 minus cosine squared x, minus minus becomes plus, sine squared x is equal to 0. And then plus C2, if I were to combine this sine squared x plus another sine squared x, therefore I can say that C1 sine squared x plus C2 times 2 sine squared x is equal to 0. Or I can say that if I were to cancel out both sine squared, C1 plus 2C2 is equal to 0. So C1 is equal to negative 2C2. C2 is equal to 1. Isn't C1 negative 2? So that means we were able to find a combination wherein not all of them are 0. So since not all of them are 0, you can see that this is linearly dependent, or that you can find a relationship between C1 and C2 wherein not both of them are 0. C1 C2x squared. Okay, so this is x squared, and x cubed. Do you think that in any way that will equate to 0? Take note that x1, x2, and x3 are non-zeros. If C1 is equal to C2 is equal to C3 is equal to 0, that means 0 plus 0 plus 0 is equal to 0. So it will only happen when all C1, C2, and C3 are 0. That's why this is linearly independent. So meaning you cannot find a relationship among the three for it to hold true unless all the coefficients are 0. C1x plus C2 x squared plus C3 x plus x squared is equal to 0. You can see here that if C1 is equal to 1, C2 is equal to 1, what will C3 be so that that becomes equal to 0? Am I correct in saying that if C3 is negative 1, this combination will give me 0? Therefore, they have a certain relationship wherein it holds true. So this is linearly dependent, meaning those variables, those solutions are dependent on each other or dependent on one another for it to hold true. You found a certain combination of coefficients. So let's just try. Determine whether the functions are linearly independent or dependent. So in here, I can say C1, F1, C2, F2, C3, F3, plus C4, F4. Okay, so this is what we're checking. You notice that C1 is e to the negative x. F2 is x squared minus 2, and then both of them are multiplied to e to the negative x. If C1 here is 2, there will be a multiplier 2 in here. And then if I add the 2e to the negative x to this, it will cancel out. If C2 is equal to 1, okay, this is just x squared minus 2 e to the negative x, but then that cancels out with this. What will be left is x squared e to the negative x. Okay, I have that. So I can say that C3 can also be equal to 1. But then you might ask, why is there a sign? Can I say that C4 is equal to 0? If this is the combination, will this hold true? This one, you're correct. It's negative 1. Will it hold true now? So isn't it that if there is 0, it's linear independence? Let's go back to the definitions. According to the definition, number 2, if the constants, not all 0, can be found such that the above equation is satisfied, then the function is linearly dependent. So not all of these are 0. Only one of them or some of them are 0. So that means this is linearly dependent. Here, C1 F1, C2 F2 is equal to 0. Take note that one is e to the x, the other one is e to the negative x. So if this occurs, in no way, because e raised to any number, so long as the number is real, not infinite, it will always give you a value. It will never be negative. So that means for this to hold true, C1 and C2 should be equal to 0. That's why this is linearly independent. So a recap. When does it become linearly dependent? When not all of the coefficients are 0. So when you find a relationship among the coefficients and not all of them are 0, it's called linearly dependent. So meaning they depend on each other's relationship for this to hold true. Whereas if no other relationship apart from it becoming or having purely zeros as coefficients, that means they are independent. So let's solve for the determinant of a matrix. But what is the determinant first? Let's go to the definition. A determinant is a representation of a matrix with a single number. So basically, a determinant is just one number that represents the whole matrix. It is also a characteristic of a square matrix, meaning other matrices, if they are not square, they don't have determinants. And how do we write determinants? Either we say there det of A, or you see two vertical lines. So this means the determinant of A. In here, I give you two matrices, a 2 by 2 matrix and a 3 by 3 matrix. So for matrices, let's just recall. For matrices, you have to remember that you have what you call the parts of the matrix. So the horizontal arrangement in the matrix are what you call the rows of the matrices, and then the vertical arrangement are called the columns. So rows, we represent this by letter M. Columns is represented by N. Therefore, the dimension of a matrix can be stated as M by N. So M number of rows multiplied to N number of columns. So that tells us the size of the matrix. So in here, you have a 2 by 2 matrix. How do we solve for the determinant? Basically, what we do is diagonal multiplication. That's one of the most common ones. But of course, there are other methods called the expansion by minors or cofactors, but we will not deal into that. Let's just go to the diagonal multiplication. So here, the determinant of a matrix, let's just say determinant of A, is the sum of the products of primary diagonals minus the sum of the products of the secondary diagonals. So what are primary and secondary diagonals? So this one, that one there, is what you call the primary diagonal. And then this one here, it's not straight, this is the secondary diagonal. So let's just try. It says there, the determinant of A, so we can write it like this, is the sum of the products of the primary diagonal. So 2 times 3, 6, minus the sum of the products of the secondary diagonals. Negative 2 times negative 1 is 2. So that means it's 4. The determinant of A is equal to 4. All right, it's easy because it's 2 by 2. Let's go to the 3 by 3 matrix. The problem with the 3 by 3 matrix is that if I pass a line here, let's just say this one, to represent the primary diagonal, and then another line, another diagonal to represent the secondary diagonal, this does not cover all the numbers. For determinant to work, all the numbers have to be considered or have to be covered. So let's just say this is the first column, the second column, this is the third column. What I would do here is, or what we usually do is, we copy the first 2 columns and then extend that. So the elements or the numbers in the first 2 columns are 1, 0, 0, 2, 4, negative 3. So those are the elements of the other columns. So now, let's draw an extended primary diagonal. So this one, okay, and then this one. All right, so I have sort of 3 primary diagonals. We have just 1 primary, but the others sort of are similar because they're inclined to the left. And then let's draw the others, the secondaries. So when we look at this, we have covered all the numbers. Some of you might ask, we have not crossed the 0 here. Yes, we have, because the 0 here is actually the 0 that I wrote there. And then some of you might say, sir, we did not cover the 4 on the extreme right. Yes, because that's column 2. Take note that in the original column 2, that 4 was already crossed. Now all the numbers have been crossed. So here, the determinant of B is actually the sum of the main diagonals. So let's go to the main. 1 times 4 times 2 is 8. Plus 2 times negative 1 times 0 is 0. Plus 3 times 0 times negative 3 is 0. Okay, we're done with the main. Let's go to the secondary. 0 times 4 times 3 is 0. Negative 3 times negative 1 times 1 is 3. 2 times 0 times 2 is 0. So meaning 8 minus 3. 5 is the determinant. So 5 is the number that is equivalent to your matrix. One of the reasons why getting the determinant is important is for this next topic, which is solving for the Wronskian. So by named after Joseph Maria Henne Wronski. Do you remember the principle of superposition? So you may have different combinations, and then when that's equal to 0, those are your solutions. So in here, according to the Wronskian, what we do here is if you have two functions here, and then, two separate functions, and then two separate coefficients, what you do here is you write the functions at the bottom. And then you get the first derivatives of each to form a 2 by 2 matrix. And then, if it's three unknowns or three functions, you write them down. Solve for the first derivative of the functions above. Solve for the second derivative of the functions. So you'll get this. It forms a 3 by 3 matrix. And according to this one, the functions 1, f1, f2, and f3 are linearly dependent if the Wronskian is 0. They're linearly independent if the Wronskian is non-zero. So this is another way of knowing whether the solution is linearly dependent or independent. So let's try. According to the Wronskian, write this. Sorry, so let's just write the whole function. 3 sine of 2x, and then 4 sine of 2x. Guys, what's the first derivative of 3 sine 2x? Because according to this, first derivative and then first derivative, 6 cosine 2x. So for the Wronskian determinant, it's basically first diagonal or primary diagonal minus the secondary diagonal. So the primary diagonal, 24 sine 2x cosine 2x minus 24 sine 2x cosine 2x. The Wronskian gives us 0. According to the definition, when the Wronskian is 0, what do you call this? That's linearly dependent. Now here, so you see 3, you can solve for the Wronskian of the 3. 1 sine 2t cosine 2t. So you're asked to solve for the Wronskian determinant. The derivative of 1 is 0. So this is 2 cosine 2t. This is negative 2 sine 2t. And then derivative again, that's 0. Negative 4 sine 2t. This one is negative 4 cosine 2t. Now, this is a 3 by 3, so that means we might need to copy the first two columns. Negative 4 sine 2t. All right. So let's get the determinant. Let's solve for the primary diagonals first. Sorry, it's a bit the line is a bit wonky. All right. So for this one, 1 times 2 cosine times, so that's negative 8 cosine squared of 2t, right? And then the other one is plus 0 plus 0. We're lucky because there are zeros that would cancel them out. Next, let's go to the secondaries. Okay. So for the secondary, minus, it's 0. It's plus 8 sine squared 2t plus 0. So in here, negative 8 cosine squared 2t minus 8 sine squared 2t. If I factor out negative 8, I'm left with cosine squared 2t plus sine squared 2t. What is sine squared plus cosine squared, guys? 1. So that means the Wronskian determinant is equal to negative 8. Since it's not equal to 0, what can I say? That this is linearly independent. Again, let's go to the definition. When the Wronskian is non-zero, linearly independent. So that means there are two ways in solving for the dependence. Either you assign the letter C's, or you can solve using the Wronskian determinant. With me, I like the matrices better, so I usually do this. So now that I have shown those to you, the methods in determining linear dependence or independence, let's go to the next. This one's just easy. I'll leave this to you. Or so yeah, maybe we can do this. So let's try. E to the t, e to the negative t, e to the 2t. So at the bottom, it's e to the t, negative e to the negative t, 2e to the 2t, and then e to the t, this is e to the negative t, 4e to the 2t. Okay, so let's copy the first two columns. All right. So let's go to the primary diagonals. So that one there, and this one here. So when you multiply those, negative 4, right? Do you remember? E to the A times e to the B is e to the A plus B. You remember this? So basically just add. I didn't see the negative earlier. So plus 2 times e to the negative t plus 2t plus t plus e to the 2t plus t minus t. So that's the first group minus the second group. For the second group, let's draw the secondary diagonals. E, so there's a negative sign, to the t minus t plus 2t. And then 2e to the negative t plus 2t plus t. And then positive 4e to the 2t plus t minus t. All right, let's fix how it's written na lang. 4e to the 2t plus 2e to the 2t plus e to the 2t minus negative e to the 2t plus 2e to the 2t plus 4e to the 2t. All right. So if you factor out, guys, e to the 2t, what happens? Right? Negative 6. So that means it does not become 0. If it does not become 0, linearly independent, right? Because according to this, if it's non-zero, it's linear